Afternoon, everyone. Welcome to the third talk, the colloquium series, SN Bose colloquium series on quantum materials and devices. It is a great honor and pleasure for me to have today's speaker, Professor Subir Sachdev from Harvard University. All of you know him, but as a formality, I'll introduce him. Professor Subir Sachdev is Herschel Smith Professor of Physics at Harvard University, USA. A renowned condensed matter theorist, he is known for his theories on critical and topological states of quantum matters, as well as for developing the Syk model, which has provided a connection between the condensed matter models and physics of black holes. His research interest includes theory of spin liquids, high temperature superconductivity, and evolution of strongly correlated matters on ultra cold atoms. He is awarded with many important prizes, including Solon Fellowship, Lars Onsager prizes, Dirac Medal, etc. Many. And he is also honorary fellow of Indian Academy of Science, foreign fellow of Indian National Science Academy, India, and also elected member of American Academy of Art and Science. With this, I request Professor Subir Sachdev to present his colloquium. Sir.
Okay, thank you very much for inviting me and for the very kind introduction. All right, so this is a series on quantum materials and devices. So I am going to assume most of you are condensed matter physicists, but hopefully you'll find some of the discussion on black holes of some interest, because I'll argue many of the questions that we have to address are quite similar. And please don't hesitate to raise your hand and ask questions at any point. Okay, so I'll begin with a general introduction to the problems that have motivated quite a bit of my research with a class of metals that are now being called Planckian metals. And then I'll give a general introduction to black holes and the many outstanding problems there, and then proceed. Okay. So to begin at the very beginning, we have a very successful theory of electrical and thermal transport in metals, in a simple metal like copper. And the central concept in this theory is the existence of quasi-particles. That you can think of the electron as just dressed by some set of excitations around it. And that dressed particle or quasi-particle can move almost independently through the entire crystal. Now, of course, quasi-particles do scatter off each other, and the scattering time diverges as temperature goes to 0 as 1 over temperature squared in simple metals. And for this, so of course, for the quasi-particle concept to be well defined, the scattering can't be too frequent. Otherwise, the quasi-particles make no sense. And if you try to apply a sort of an uncertainty principle to that kind of reasoning, you find that there's a limiting time, tau, which is now being called the Planckian time, which is just h power over kBt, because it only involves Planck's constant and temperature measured in units of energy. So as long as this tau is bigger than h power over kt, everything is fine. And effectively, transport in a simple metal is ballistic over these before this long time, after which it becomes chaotic. Okay. However, in many modern materials, including say the high temperature superconductors like YBCO here, here's the phase diagram as a function of electron density and temperature. There are a lot of interesting phases at low temperature, including the superconducting phase. But my focus will be really on the higher temperature regime. And again, I won't go into the details of these different phases, just to say here that the Fermi liquid is where the quasi-particle description seems to work. And the focus here is on this intermediate temperature regime, which is called the Planckian metal. So I just show you some recent, so I'm going to focus on that. Some very recent paper just this year, which measured the scattering time by measuring the angle-dependent magnetoresistance in one of the high-temperature superconductors in this regime. And what they found was that there was an isotropic component of the scattering time, this red line, which in fact is shown here as a function of temperature, and it's essentially a linear function of temperature, and also the coefficient here is about 1. So what we're seeing here very clearly is the scattering time is so short that there's no sense of quasi-particles. But also, quite remarkably, the scattering time is just given by the Planckian time. It seems to be independent of any system parameters or energy scale, which is quite remarkable because when you do have quasi-particles, the scattering time depends very much on all the interaction scales in the system. So this is just the latest in a long series of observations, not just in the cuprates, but in other materials. I just show you 2 other recent observations. This is another cuprate. This is in fact magic angle twisted bilayer graphene. Very different system, but again, at this filling fraction where you get superconductivity, if you look up here, then the resistivity is a linear function of temperature, and if you try to estimate the time, it is again also very close to h bar over kt at rather low temperatures. I should say the mysterious part of the linear resistivity is not so much the high temperature behavior, for which there can be many possible explanations. It's the fact that it extends down to very low temperatures. By applying a magnetic field, you can even get it down to 0 temperature. And also that the offset here is extremely small, suggesting that these are very clean systems. And nevertheless, it seems like the resistivity is a linear function of temperature. So this really raises many questions, which I'll try to give you some answers to today, but it's by far from a closed system. I mean, many things are not understood. So what we really need is a theory for transport in the fermion system with a relaxation time, which is just Planckian. And then also want to compute not just the relaxation, but the resistivity. And almost all such systems at even lower temperatures in the absence of a magnetic field become superconductors or have some other broken symmetries. This is something I'm not going to address, but again, obviously it's a very important problem that needs to be addressed. Okay, so that's my lightning introduction to one of the central problems that appeared, let's say, almost 30 years ago now. And the questions have become much sharper because of many improved experiments. But it seems it's really quite central to understanding the phase diagram of the high temperature superconductors. Okay, so now let me just change gears and talk about black holes. So I'm not going to assume you know anything really about black holes. So hopefully I'll maintain that promise in this introduction. Okay, so what is a black hole? A black hole is a very dense astrophysical object normally, which is a solution of Einstein's theory of general relativity. So if you take a mass m, a star of mass m, and squeeze it down to a radius r, this is the Schwarzschild radius, where g is Newton's constant, c is the velocity of light, then Einstein's theory tells us that the curvature of space-time inside this horizon is so strong that nothing can ever leave the horizon. That light itself is trapped inside, and once you fall past the horizon, then there's no hope of getting out. Of course, it's a very dense object. For example, if I put in the Earth's mass, then this radius is 9 millimeters. So that's how dense you have to compress something to make it into a black hole. But there are black holes out there in the universe. In fact, now we know there's a supermassive black hole of a mass of million or billion suns at the center of every galaxy, including the Milky Way. Okay. Now, we want to think now about the effects of quantum mechanics on these objects. And this was something that was the early ideas were by John Wheeler, who made this picture, but Bekenstein and Hawking in particular published important papers where they argued that once you apply quantum mechanics, then black holes are not completely opaque. They do have, there is some information and in fact even matter and energy leaving the black hole via quantum tunneling. And one consequence of quantum mechanics is that black holes have both an entropy and a temperature. Roughly, you can think of this as an entanglement entropy of quantum degrees of freedom inside and outside the black hole. So if you're outside the black hole, since you have no access to the inside degree of freedom, your any qubit that you may have outside the black hole is essentially random and hence the temperature. Okay, so this is the formula that Hawking gave for the temperature of a Schwarzschild black hole of mass m. Another remarkable property is that the entropy is proportional to the surface area of the black hole. And that seems rather unusual because no other system, quantum system, has an entropy proportional to the area. Entropy is proportional to the volume. Okay, so this picture suggests, this picture here, that it's as if the black holes have, first of all, a finite number of degrees of freedom, because the entropy is some finite number times the surface area. And these degrees of freedom are living on the surface. So that hence this picture here. Whether that's really true or not is really one of the important open question. So yeah, so they are remarkable features. The entropy is finite and the entropy is not proportional to volume. Another interesting feature of black holes is you can ask a question, what happens when you perturb the black hole a little bit? How long does it take to come back to a perfectly spherical shape? So this is a purely classical question. You could perturb a black hole by a star falling into it, for example. And very quickly, it will come back to equilibrium into a perfect spherical shape with a slightly larger horizon. And this time, is the black hole is called the black hole quasi-normal ringing time, computed by Amish Wafer actually. And this time is 8 pi GM, around 8 pi GM over c squared. Now, this work, as you noticed, was earlier, before Bekenstein and Hawking. But now you have these two formula, you notice something remarkable, that the black hole thermalization time is, again, the Planckian time, wherein you put in here the Hawking temperature. So this is a one immediate indication of some connection between Planckian metals and black holes. They both have a relaxation or thermalization or collision time, which is h bar over kT. And there are much deeper connections, which I'm going to argue now. But this is the first indication. Okay. Curiously, this is again a recent paper where people have actually measured the ringing time or the merger time of two black holes from LIGO. And they took a whole bunch of, it's a complicated analysis of the LIGO data, and they measured the time. And this picture showed that for a whole bunch of black holes, this time indeed, up to factors of pi, is just h bar is the Planckian time. So this verifies the theory. I should emphasize, however, this doesn't mean they've seen quantum effects. The time is a classical thing. It's only when you express it in terms of the Hawking temperature, which has an h bar in it, then the time has an h bar. But the h bar cancels out, at least in the gravity theory. In the quantum theory, it doesn't cancel out. Of course, it's an essential part of the dynamics of the system. Okay. All right. So can we make sense of these results? So let me just say a little bit about how one way that in the early days this entropy was obtained. So very naively, if you want to evaluate the quantum theory of a black hole, what you would say is, well, I take the classical action. I will consider black holes as the net charge Q for a reason that will become clear enough eventually. I take the action of Einstein gravity and Maxwell electromagnetism, which is a function of functional of the curvature of space-time and the electromagnetic gauge field, and I just evaluate the path integral. That'll give me the partition function, and therefore I can compute the free energy and the entropy and so on. All right, easier said than done, because this integral is simply not well defined. Doesn't even mean anything because it's full of infinities that no one knows how to control. But that didn't deter Hawking and Gibbons. They said, let's not worry about how you do the integral. Let's just evaluate the saddle point. Let's do the what you always do when you're doing a path integral. The first thing you do is look at the saddle point. And in the saddle point, you do this in Euclidean time, and you know that the circumference of the time circle in Euclidean time is h bar over kt. So that's how h bar enters into calculation, just from the periodic boundary conditions in time. And you evaluate the action, and what you get when expressed in terms of the entropy is the Bekenstein-Hawking formula, A of T C cubed over 4g h bar, where A is the area of the horizon. At very low temperatures, for charged black holes, you get a non-zero area at zero temperature. I call that A0. And so there's one over, so this is the same term here, and there's a term that's linear correction of temperature. Okay, so one should view this really as a saddle point result. So in other words, it's a 1 over G, expansion in small g. So this is the leading order result at small g. Amazingly, this result is correct, even though this path integral is not well defined, as we know today. So it was a rather bold proposal that this calculation makes sense. Okay. So I've already mentioned, so that's my introduction to theory of black holes, and it raises many questions. Okay, you've got the saddle point integral, but does this kind of semi-classical theory of gravity make any sense beyond it? Can you compute at least the fluctuation correction, the leading fluctuation determinant? And this whole calculation really has no Hamiltonian or anything in it, even though it's giving you some thermodynamic properties. Is the resulting thermodynamics the thermodynamics of a unitary quantum system with a discrete spectrum? Has to be discrete because the entropy is finite. And so is there any such system? So that's a very important question raised by Hawking's calculation. And another thing Hawking and Bekenstein talked about was the evaporation of the black hole. And this led to certain contradictions that Hawking was not able to resolve. And so this is not something I'm going to resolve today at all, or even talk about. But there's been a lot of progress on these questions recently, using some of the tricks that I'm going to discuss to address the first two questions. So is the evolution of a black hole, including its evaporation, exactly that of the evolution of any quantum system, like a cup of coffee or anything like that? All right, so that's an introduction to two very different fields of physics, with which have dominated a lot of theoretical research anyway in the last 20 years, and the many important open questions that are present there. And they seem rather disconnected, but as I've said, there is already a hint of a deep connection, which is the common Planckian time that both these systems feature in their thermal equilibration. All right, so now I'm going to come back down to earth and just talk about a particular model. And this model has taught us a lot about the first two problems, and I'll turn to that in the latter part of my talk. But for now, I'll be very specific. I'll just talk about a particular model, which is solvable, and so it helps us. It's always great to have solvable models of some exotic phenomena. So what is this model? What need does this address? Well, it's kind of clear from what I've said is what the essential ingredient in what's novel about these systems is they have a lot of multi-particle entanglement. They have many dequantum degrees of freedom, and they're leading to, so at least in the metallic case, some kind of quantum state which is compressible. By compressible, I simply mean that just by changing the chemical potential, you can make it have any density you want. And this is a state without quasi-particle excitations. So let me go back in history a little bit. So what is the origin of discussing multi-particle entanglement? In fact, it goes back to 1865. This is a picture I took of Auguste Kekulé on a snowy night in Bonn, and where Kekulé was the one who proposed the structure of benzene molecule. And benzene features what we now call resonating valence bonds. So it's got these double bonds, and these double bonds can resonate between two configurations. And effectively, this is then some kind of entanglement of 6 electrons in a highly non-trivial way. So I found this in Wikipedia. He spoke of the creation of the theory. He said that he had discovered the ring shape of the benzene molecule after having a daydream of a snake sneezing its own tail. So when I read this, I said, okay, I can say that at some point I had a dream, which is based on snakes going all over the place from any point to any point rather than just in a circle. And that analogy, it basically gives you a vivid picture of what the Syk model is. So here's the explicit model that I want to now talk about. You take a bunch of sites labeled alpha, beta, gamma, delta, on which there can be a fermion. And the only term in the Hamiltonian that's non-trivial is this interaction. So these fermions interact, but they can't hop. And they interact with this interaction matrix element, U alpha, beta, gamma, delta. And that's it. That's the Hamiltonian. Now I have to specify what these numbers are. Now if I give you a given set of numbers, this is impossible to solve for n particles. The number of states in the Hilbert phase is 2 to the n, which is huge. So beyond n equals 20, you can't even put it on a computer. So how would you solve it? Well, the observation here is that if these are independent random numbers, that's really all you need. You need these U alpha, beta, gamma to be independent random numbers. For convenience, you take them at 0 mean and have mean square value U. Then you can solve it. And you can solve it in the sense that the system actually is self-averaging. So unless you ask very, very, very precise questions of high precision of e to the minus n, it doesn't matter. You just need to take one system and you can still understand its properties just by looking at the properties of the average system because it's self-averaging. So here's a pictorial description of all those snakes. You take a bunch of sites, you take put some like fermions in them, and then they can go from any pair of sites to any other pair of sites at random with a random amplitude, and so this leads to complicated multi-particle entanglement that we want to understand, and in fact now understand quite well. Well, there's too many open questions. So that's the Hamiltonian and a picture of it. Okay. Actually, I don't have any access to the time, so just wait a minute. I'll get my my clock. Okay. All right. So before I describe this, some of the properties of this model, let's take an even simpler model. This is just a random matrix model, but viewed from many body sets. So you take fermions, which can now hop on their own rather than hopping in pairs. And hopping amplitude is Tij. And these are just, again, independent random numbers. So this is a free fermion problem. And to solve this is very simple. You just diagonalize this matrix. That's an easy job because the matrix here is just n by n rather than 2 to the n by 2 to the n as it was for the Syk model. You diagonalize the n by n matrix, you get a bunch of eigenvalues whose spacing is 1 over n. And then you fill the lowest qn of them, density, if your density is qn. Okay, and in the large N limit, if you want to compute, say, the entropy of the system, all you need to know is the density of states at the Fermi level, and this is the sum of L formula for the entropy of a free Fermi system. Gamma, the coefficient gamma is related to the density of states at the Fermi level. Okay, that's all undergraduate quantum mechanics. But now let's just take this very same system and think of it as a many-body system. So I'll plot the density of states, not of the individual eigenvalues of Tij, but the eigenvalues of a many-body system. That is, I fill a whole bunch of them. So N alpha is the occupation number, which can be 0 or 1, and this is the many-body state. Okay, and for exactly the system, for one fixed system, I don't know, size 20 or so, something like that, you diagonalize it, you get 20 eigenvalues, then at some chemical potential, and then you compute the 2 to the 20 possible values of this this number, and you plot all of them here. Okay, so this is what you get. This is the many-body density of states. So what does this look like? Let's focus on the low energy part, where the energy density is finite, but it's still small. So there, we know the answer. The density of states is just the exponential of the entropy. I told you the entropy in the canonical ensemble, so you just convert it to the entropy in the microcanonical ensemble, easy to do, and you get this answer here. E to the 2n gamma e square root. The e is of order n, and there's another factor of n, so the whole thing is of order e to the n, as it should be. The density of states is e to the n, meaning the energy level spacing is e to the minus n. And why is the energy space? Well, I'll come back to that one second. So now let's zoom in to the bottom of the band over here. So here's the actual eigenvalues, and here's an even finer view of them. So what you can notice right away is at the bottom of the band, the energy level spacing is much larger than in the middle of the band here. And why is that? Well, that's because at the bottom of the band, something very simple is happening. If you take the ground state, that's just, all the states below the green line occupied. Then what is the first excited state? Well, it's something very simple. You either add a particle on this level or you remove a particle from that level. And that will cost you energy 1 over n. So initially, the ground state and the low-lying excited states are very closely related to each other. As n goes to infinity, you're just removing or adding a few quasi-particles. So these are almost the same state. But since you're making this perturbation using quasi-particles, the energy level spacing is much larger here. Now, why is the energy level spacing here so much smaller? Why is it e to the minus n rather 1 over n? It's so much smaller here because you pick one level, they say this level and the next level, and you look at their quasi-particle occupation number, they're entirely different. In one level, you have one set of quasi-particles, another one, you have totally different set. So they're very, very different. They change chaotically from one to the other, but each has a definition, has a decomposition in some quasi-particle basis, at least at low temperatures. Whereas here, all these states are very, very similar, and they have a large spacing in energy. Okay, so now with that introduction, let's go to the Syk model and do exactly the same thing. Let's just do numerically the computation. And this is what the many-body density of states looks like. Here, there is no single particle density of state to talk about because there are no single particle states that are well defined. And what is this? So we know a lot about the functional form of this. I'll just state some of the results. So this d of e, where the energy density is finite. Remember, for the free particle system, I have the square root of 2n gamma e. That's still here. And so that corresponds to an n gamma t in the entropy as a function of temperature. But what's new is this constant here, S0, which is a constant we computed in 2001. This is essentially a zero temperature entropy. Okay, so there's a prefactor here. Both are of order n. There's a prefactor, which when you're up here, it doesn't make much of a difference because the entropy is extensive anyway. But let's go to the bottom of the band. What's happening at the bottom of the band? Well, there you find this factor is still present, and there's a correction we won't worry about. And now, so what's different here is that the energy levels at the bottom of the band are also exponentially close to each other, e to the minus n. And that's why you have this huge density of states. Note there's no degeneracy. So this is not like a ground state entropy. There's no degeneracy at all. But you have all these energy levels which happen to have energies that are really close to each other. And that immediately tells us there cannot be any quasi-particles because there aren't enough quasi-particles to go around to have so many states because the number of quasi-particles just n. So how can you just add and remove quasi-particles and get so many states right next to each other? And so if you look at the wave function of this state and the next state and the next state, they're completely different from each other in this exponentially large Fock space. So there's huge amount of chaos here, and we really have no simple description that I can tell you about these states, or even what their energies are. But if you are satisfied with some kind of average over this, and so now you can see why the self-averaging is so good because there's so many states, and these are exponentially small, and this is a relatively small system, so you can, essentially exponentially dense. If you're just interested in the average of over these very, very, very dense states, which is really any reasonable experiment would be sensitive to, then actually you can compute everything to high accuracy. And one of the things you can compute is a crossover from this to this. And this comes from a theory of quantum gravity, in fact. And I'll give a little bit more information on where that comes from in a minute. And this particular cinch density of states is actually playing a crucial role in many recent studies of quantum gravity and strange configurations, including wormholes. And what is this? So I can convert this density of states to entropy by just computing the partition function. And that entropy gives you is the correction is this is 3/2 log u over t, which is now the 1 over n correction to this, leading a large end result. Actually, the way this computation was done was the other way around. You first computed the entropy, and then you figured out the density of states by inverse Laplace transform. Okay. All right. So that's one set of remarkable properties of the SYK model. It has, exponentially large number of levels at low energy, and there is no quasi-particle interpretation of the low energy states.
Subir, may I ask
Yes.
a question?
Yes, please.
Yeah, this is Brijesh here. So you say that the ground state is still unique, it's non-degenerate. So what that exactly is? And just another part of the same question. If this is so, then it reminds roughly of the Kagome spin half system where you have, of course, an unclear ground state which nobody knows and an extremely large, exponentially large number of low-lying singlet states. So just your comment on the ground state of your model and some, the origin of exponential degeneracy.
Those are actually great questions. I'm noticing that the light in my room has changed so you can see my face. So let me just turn this thing off. Okay. Maybe it's, whoa, no, that's even worse. Okay. So the point is that, so the Kagome system, for example, there is a ground state degeneracy in some Ising model or something like that.
Yeah.
So that in the Kagome system, that's really a degeneracy of the ground state, an exponentially large degeneracy.
No,
it's
but
also
the quantum
present
case,
in
the
the Ice model.
Heisenberg case. But in the Heisenberg case, there is apparently no degeneracy in the ground state, yet there is an exponentially large tower of states, yes.
Right. So if you take a classical model and you fine tune the coupling, then you can get, like in the ice model, then you can get ground state entropy But that entropy is highly non-robust. Any perturbation will lift it, and then you get, essentially unique ground state or a fourfold degenerate ground state, and then if you look at the low-lying excitations, they will be quasi-particles then spaced by 1/n. So there is no remnant there in the Kagome model of either the ground state degeneracy or the low temperature entropy. So here, this is completely different. First of all, what is the ground state? I don't know what is the ground state. It's some complicated wave function. And it could have like a twofold degeneracy if you have some parity or some other symmetry like that. But generally, it's non-degenerate. But the fact that you have an exponentially large number of levels at low energies, that the zero temperature entropy is finite or extensive, is robust. You can change the couplings as you want. This is just one system. I'm not doing any average. I pick one set of couplings, and you get these levels. You pick another one, you still get it. So this particular zero temperature entropy is highly robust, whereas the Pauling ice entropy is exactly the opposite of robust. Anything will lift it immediately. It'll go away.
Understand.
Okay.
Just one small other question. Go ahead, please.
No, you go ahead.
Okay. Now, one other question which sort of came to my mind. Although it's by construction a many-body model with actually no single particle term except for the chemical potential, I mean, you must have still calculated the single particle local density of, it's like C dagger C, propagator, and it's
this model.
Just to see what exactly it looks like in this model, in your Syk model.
Absolutely. So while you say, that was my next slide. That was my next slide.
Okay, good.
Okay. Any other question? I'll show you. I answer that question in the next slide.
Okay.
That's
okay,
good?
go ahead.
Okay. All right.
Yeah.
All right. So now, so there's a few other things you can compute. In fact, this is what we first computed, was the quantities here. So for example, if you compute the single particle Green's function, then you get a single particle density of states that diverges as 1/square root of energy at zero energy. If you compute it at finite temperature, you find that there's this function which smooths this thing out on exactly the Planckian time. So you get a Planckian time, and the coupling U doesn't appear anywhere in this function. It's a universal function that, in fact, you can compute exactly. So this is then the emergence in this system of the Planckian time very naturally. Now, in fact, some of the computations I showed you for the density of states, which were done by many people, not by me for sure. If you want the full list of references, you have to look up this review article. And the way these things arise, the fact you have the cinch density of states and so on, it comes from the presence of looking at the leading irrelevant operator. So this particular scaling is related to some scaling conformal symmetry of the theory. But you have to go beyond this conformal symmetry, look at corrections to it. And there's a soft mode, which has a huge effect. And that soft mode, it sort of has a flavor of gravity. It's a theory of time reparameterization. So if you take the path integral of the Syk model and just look at the saddle point fluctuations, you find it's very naturally expressed in terms of the soft mode. And you can read much more about this in our review article. So this soft mode, in addition to giving you the cinch density of states, also has another important consequence, as was pointed out by these distinguished scientists, that if you compute something called the out of time order correlator, this is a diagnostic of some chaotic behavior in terms of correlation function. I mean, I told you about the chaos in terms of the eigenstates being so close to each other and unrelated to each other. Here, in that same chaos gets manifested in some correlation function as the growth of randomness, and the growth appears at a universal rate, which is given by this Lyapunov exponent, which turns out to be exactly 2 pi kT over HR, which is again the inverse of a Planckian time with a factor of 2 pi. And in fact, there's a proof, quote unquote, by Maldacena, Schenker, and Stanford that this is the maximum possible frequency. And any other system should have, in particular system with quasi-particles, should have a Lyapunov exponent that's smaller than this Planckian time. Yeah, okay, this I've already mentioned. All right, so that's a summary then of the SYK model. Actually, this would be a good time for questions. So right now, hopefully, at least I talked about a well-defined model. I told you about its properties. I didn't really give you any details of how the computations were done, but you can read about the review article, or you can come to the course that I'm teaching at ICTS online these days, and I will be covering some of these topics in that course over the next few weeks. Anyway, so any other questions? Okay, so now let's, now that we understand one model. Yes, go ahead.
So, in the black hole part, you talked about how all the degrees of freedom are on the surface of the black hole. That's our current model, right?
That's just a picture meant to be an intuitive picture. It's not to be taken literally.
Okay, but if I take all the degrees of freedom on the surface, what should be inside the black hole then?
Yes. So like I said, it's not to be taken literally. You know, you should think of it kind of like a duality. So there is one formulation of the theory, which is uses qubits on some surface, some imaginary surface, really. So that theory is expressed entirely in terms of qubits. And then there's another theory, which is expressed in terms of the metric of space-time, which lives in one higher dimension. So, and these are two different ways of talking about the same physics. So in fact, correlation functions in one can be mapped onto correlation functions to the other. So this is you know, in the spirit of something like a Kramers-Vonnier duality, the Isaac model, but this is much more non-trivial because it's duality between two dimensions and 3 dimensions. But nevertheless, so that's called the holographic duality. And in fact, I'm going to say a little bit more about that in a minute. Yeah. Okay, so that's in fact precisely the next topic then. How does the SYK model tell you something about black holes? And now you'll see the duality, the dimensional reduction go in the opposite direction. So I'll start with the theory of gravity. So this is the theory of gravity in 3+1 dimensions. And I just summarized the result of Gibbons and Hawking, where you just looked at the saddle point of the action. So now you'd like to do the path integral about the saddle point, at least the Gaussian fluctuations about the saddle point you can ask can be done. So Gibbons and Hawking didn't try it because they thought it wouldn't work. And it wasn't until relatively recently that actually people figured out how to do that. And it's simpler for the case of charged black hole. In fact, as I'll refer, Ashok then made some important contributions about this some time ago also in thinking about the fluctuation determinant about such black holes. But for now, let me notice that if you look at this term, which is an expansion in small g, it's some very large number, constant plus term linear in temperature. And I just remind you, that's exactly what I had for the SYK model. The entropy was a very large number, which is n times a constant plus gamma t. And now I'm going to claim is that this correction that we found in the SYK model is also present for a black hole, for a charged black hole, generally. Okay, so let's see what is the reason for that. Okay, so first of all, there's a reason I focus on charged black holes is because they have some a rather simplifying feature. If you look at the solution of Einstein's equations and the Maxwell equations for a charged black hole, so this is really, you know, classical theory. I had to go through it myself. I have gone through it. It relies on not much more than basic general relativity. We solve the equations for a charged black hole and look at the metric of space-time. And what you find is that when you're far from the horizon of the black hole, then the metric of space-time is four-dimensional. It can be either flat or anti-de Sitter space, it doesn't matter. But as you get near the horizon of the black hole, then there are three spatial directions. There's the radial direction, and there's the two angular directions, omega 2. And it turns out that the metric factorizes. There's one part, which is the radial part, which is just, in fact, has some fixed radius and no other dependence on angles. R sub h is the horizon radius. And so that's the S2. But where all the interesting time dependence in quantum mechanics is in the radial part only. So there's the radial direction zeta, and then there's time. And this turns out to be the metric that pops out of the solution of Einstein's equations near the horizon of a charged black hole. There's also some electric field, which is related to this gauge field. Of course, by Gauss's law, there has to be electric field. There's a net charge, so there has to be electric field outside. Okay. So what is this metric? So this metric turns out to be a very special metric. It's called anti-de Sitter space 2, ADS2. And it's exactly the metric in Euclidean time of the uniformly curved Lobachevsky space, the hyperbolic space. So it's like a sphere, except you change one of the metric signs from plus to minus, or more than one. Okay, so just like a sphere has an SO3 rotation symmetry, this metric has an SL2R, which is also a three-dimensional group symmetry. It's like a rotational symmetry in hyperbolic space. So it's a highly symmetric space. And in fact, this symmetry, SL2R, is identical to the conformal symmetry of conformal field theories, and hence the connection. So this ADS2 part, in fact, is also the low energy theory of the SYK model, amazingly. So what happens here is that you can forget about the radial part, other than the presence of the uniform mode, the size of RH, and or you do all your gravity in these two dimensions. And now gravity in two dimensions has no gravitons, so you can gauge away almost everything. But what you find then, when you look at this very carefully, you can't quite gauge away the gravity. There is a graviton, but it's on the boundary. The boundary where you go from two-dimensional space-time to four-dimensional space-time, there's a boundary layer. And all the action is on the boundary. So this is a partial answer to the question that was just asked. In this case, anyway, you can see that all the dynamical degrees of freedom are on the boundary. All right, so you can reduce then and take a conventional low energy limit of this theory to this theory. This was done by these people here, although in principle this could have been done a long time ago, but it's essentially calculation classical gravity. And then you gauge fix the gravity in the bulk, and in the end you find that the whole theory can be written as an action just in one time dimension. So what's left of the boundary graviton is just a time reparameterization f of tau. So in the end, you have a quantum mechanics problem in 0 + 1 dimensions. And this f of tau, roughly speaking, is just describing the fluctuations of this boundary in time. Actually, it's really the radius fluctuating in time. Okay, so you get some action. And amazingly, the action you get here is exactly the action you would get if you started from the SYK model and did all these low energy steps, starting from the SYK Hamiltonian. And that particular calculation is described in great detail in the review article, and which I will discuss in my course. Anyway, so now you have this path integral, which is now, fortunately, just an ordinary path integral in one dimension. It's like, almost like quantum mechanics. So you can, and this turns out you can evaluate this path integral exactly, and that is how you get this 3/2 log t correction. So this appears both for the for the charged black holes in 4 dimensions, 4 space-time dimensions with charge Q at low temperature, and also for the SYK model. And now if you take the inverse Laplace transform of this entropy, you get the density of state I just showed you. There's another correction that's temperature independent that actually corrects this term. So it's not important for anything I'm saying, which was computed by Ashok Sen. But this additional contribution, the log T contribution, comes from this boundary graviton that Ashok didn't consider. Okay, so now I can at least give you some summary then. So this particular entropy, now argued, applies also to a black hole. Now this entropy, if you now compute the density of states from it, it gives you this density of states. This density is a continuum. It's some smoothing of this function here, which is just made up of a set of discrete delta functions. So when we do semi-classical gravity, we get the smooth density of states, which get this density of states. And so that's okay. That's the answer. But should we believe it? Is that an answer of a quantum system? Just from the fact that it's smooth, tells us that it's kind of a little bit fishy, because you have a finite quantum system of size n. How can it have a continuous density of state? It has to have a discrete set of delta functions. So semi-classical gravity doesn't know anything about, in that sense, of the discrete set of delta functions. However, amazingly, we have now shown that there is a quantum system. In particular, if I take a SYK model with a fixed set of couplings, any set of one set of random couplings, I do get exponentially dense set of levels, which are discrete. Of course, precisely those energies depend upon precisely the couplings I've chosen. But if I'm satisfied by just averaging this over the exponentially small spacing, then I will get exactly the same density of states. So we have at least one realization of this picture then. I've shown you then this SYK model, which is a set of fermionic qubits, which has a discrete spectrum, which is completely unitary, and whose coarse-grained density of states agrees perfectly with the semi-classical gravity. So that, at least as a matter of principle, this answers some of the important questions raised by Hawking's and subsequent calculations. This is not to say that I actually think in our universe there's SYK models everywhere. I don't think so. That's certainly not true. It's just saying that it's an example of a system, a unitary quantum system, that can give exactly the density of state that gravity seems to predict. Probably at high energies, we have string theory, but string theory, eventually when you go to low enough energies for a non-supersymmetric black hole, should have the same features. Oh, that's just a hypothesis, anyway. Let me also mention very quickly, there are also other computations of density of states of black holes, at least of the very low energy density of states. And these involve string theory and supersymmetry, not just at high energies, but also at low energies. And they give you, in fact, a very different density of state. They give you a delta function. So there you have an exact degeneracy, much like the degeneracy that Brijesh and I were just discussing. Here, the degeneracy is imposed by supersymmetry. And there's even a gap in the spectrum. And so the number of degenerate state there is indeed exponential of A naught over G. And if you compute the corrections, then the corrections will be such that this number is an integer. It has to be an integer. There's no such constraint for anything I did for the I described for the SYK model or the semi-classical gravity. But here in string theory, you're actually computing an integer in some approximation. But actual black holes, if they don't have low energy supersymmetry, have a very different density of states. Okay. All right. So now I'm now in more comfortable grounds since I've told you almost everything I know about black holes, and hopefully I didn't make any mistakes. So now let me take the insights of the SYK model and finish up by talking about connections to the models that we're really interested in. And I see that I'm almost out of time. Okay. So maybe I'll only talk about part A and maybe not about part B. We'll see. Is that okay? So how much time do I have, Manoranjan?
So it's still 5 minutes.
5 minutes.
But
Okay.
I mean, you can go ahead. I mean,
Okay. All right. All right. So I want to talk about the Planckian metal, where I start from, let's say, the insulating side. So what's a simple model of the cuprates? Well, it's electrons hopping on the square lattice. At zero doping, you have an antiferromagnet, which can have spin exchange J, and then you can remove some holes, and then they can move around in what's called the TJ model with prohibiting double occupancy. So we take exactly that model, which of course many people have been trying to solve, but we have found that you can make a lot of analytic and numerical progress where you just take the Tij and the Jij to be random numbers. So I'll just show you some numerical results of what happens when you do that. And all sites coupled to all other sites, like in the SYK model. But this is a very different model because it's got this projection operator, which projects out doubly occupied sites. So it's not solvable like the SYK model as written. Okay, so what you find as a function of doping is that very low doping in this particular model, instead of having an antiferromagnet, you get a spin glass, as in Parisi's model. And at high doping, you get a Fermi liquid. And very interestingly, right in the middle, you get Planckian metal with SYK-like dynamics of the fractionalized spin-on. So it's like a SYK where the fermions are not electrons, but spin-ons. And furthermore, you can compute the transport, and very beautifully, you get linear T-transport. We don't fully understand where this comes from, but if you take a certain large M theory where you generalize SU2 symmetry to SUM symmetry, then you find that, again, it's the same time reprogrammization mode that's been a central actor in everything I've said that gives you this linear T-resistivity with, in fact, very close to Planckian time behavior. All right, so that's one numerical progress and analytical progress where we are, at least for the random model, we have an example now of a Planckian metal down to very low temperatures. Another model that people have used over the years quite a lot to describe the Planckian metal, starting from the large Fermi surface side, is where you take your Fermi surface, Fermi liquid, and you couple it to some critical boson. This could be a gauge field or some Ising nematic order parameter or some other T or P breaking order parameter, and ask what happens to this theory when you take a bunch of quasi-particles and you scatter them very strongly by having essentially a zero energy boson. What happens there? Okay, so that's been studied a great deal, and it yields a state without quasi-particle excitations once you couple the fermions to the boson. But this is not a systematic theory. As Syk Model famously pointed out, it's not under control. So even for this theory, which we'd have to solve, there is no control method. And recently we pointed out that there's a way to control it, this particular theory, by just putting in some labels, I, J, and L, that run from 1 to N, and making this, and then you have a coupling G, I, J, L. But now you take this coupling to be a random number. Notice there's no disorder in space, it's all in coupling space. And now the idea is that it doesn't really matter what coupling you pick, they all flow to the same low energy theory. Just like in the SYK model, it doesn't matter which coupling you pick, just pick one. It has the same properties. And then, however, you can make your life simple by just computing the average property, because that's a lot easier to compute. So that's exactly what we did. And we showed that actually, yes, this works. This is with Ilyas, postdoc at Harvard, Hugo, who's a student, and Avishkar Patel, who's now a postdoc at Berkeley. So this, you get a systematic theory of a non-Fermi liquid, where you still have a sharp Fermi surface, but the spectral function is diffuse in frequency space. If you look at the Green's function on the Fermi surface, that's again very similar to the SYK model with some function f you can compute exactly at large n. And the exponent, instead of being 1/2, is now 2/3. And very recently, in work by Maria and Avishkar, we also computed out amount of correlator. This hasn't been written up yet. And again, it's very similar to the SYK model to get the maximal value of 2 pi kt over h bar in the large n limit that we're able to compute it. All right, so that looks exciting, a very promising theory for a Planckian metal, as many people have thought over the years, and many people have claimed also. But there's just one simple problem. If you actually compute in this theory the conductivity, the resistance is 0, or the DC conductivity is infinite. So there's a delta function here, a pesky delta function that people conveniently ignore, but it's there in this theory, no doubt about it. And it comes from the fact that this theory has no Umklapp, and momentum is exactly conserved. I mean, you can put in Umklapp if you regularize on a lattice, but then the Umklapp processes are exponentially weak. There is some non-Fermi liquid behavior, but it only appears in the optical conductivity, not in the DC conductivity. So how do we fix this? So can this thing be rescued as a theory of the Planckian metal? My own opinion has oscillated over the years. I'm now starting to think it can. And what do you have to do? Well, learning from the SYK model, we got to put in some disorder, which is always present in the system, spatial disorder. And so the naive thing you want to put in is a Vij, some potential scattering of the fermions. This, the entire theory of weakly disordered metals and disordered Fermi liquids is based on this kind of potential scattering. You can put this in here, but then you find it doesn't do much, actually. It just gives you some residual resistivity, and that's about it. So the key idea here, this is a new idea, not yet written up. What you got to do is add also disorder in the interactions. You have to have spatial disorder. You have to put in the next subleading correction. But the disorder is in the interactions, not just in the potential. And again, this is very much the spirit of the SYK model. That's the disorder in the Jij that gave you all the interesting Planckian behavior. And in fact, even in the TJ model, the linear resistivity. So now you have a model with all three terms that you can try to solve, and we are in the process of sorting all the different regimes out. And what you do find, that there's a clear-cut regime where you get the resistivity, which is linear in temperature, where this C tilde is actually given by the G prime. And the potential scattering Z just only gives you the residual resistivity. So anyway, this is something very much work in progress, something you're very excited about. And I think this is getting fairly close, I hope, of some kind of reasonable, realistic theory of the Planckian metal. Okay, so let me conclude. So the SYK model, love it or hate it, you can't deny that it's a solvable model without quasi-particle excitations. It has Planckian dynamics and maximal chaos, and this makes it a very useful thing, at least to study, if not to apply to realistic systems. All of these wonderful properties are actually related to a theory of quantum gravity, amazingly, which lives on the boundary of a two-dimensional anti-de Sitter space. I didn't tell you how, but come to my course if you want to learn more about this. And so then you apply these ideas, and they have a rather, in fact, direct application to gravity. And they show you that this -3/2 log T is a universal correction to the entropy of any charged black hole. And further work using these 2D gravity ideas, which I have certainly not contributed to, has led to progress in the structure of entropy of evaporating black holes. Then I very quickly talked about two models of a Planckian metal. One is not as realistic, which is a random TJ model, which doesn't have superconductivity, but it seems to have almost everything else that you observe. Even quantitatively works quite well. And we are now thinking about a more realistic model of a Fermi surface coupled to a critical boson that definitely has some nice features like Planckian time dynamics and the Lyapunov exponent. But the resistivity is the hardest thing to compute, and it involves really thinking about subleading operators. But the interesting thing is that in both cases, it seems like it's the random interactions are the key to get the linear resistivity. Okay, thank you.
Thank you. So let's thank Professor Sachdev for excellent talk. And now I hope you'll take some more questions.
Sure, happy to.
Yeah. So now it's open for the question. Please go ahead. Yeah.
Yeah. Someone has. Can I ask a question? Yeah. Yeah. So you mentioned that oh, there's an echo. I think. Okay, you mentioned that
just go ahead.
In the twisted bilayer graphene, you have this linear dependence of the resistivity down to very low temperatures.
Yes.
So is that also the randomness in the interlayer coupling which is responsible for it? Right at the beginning, you mentioned.
Yeah. So this is what I showed you.
Yeah.
The honest answer is I don't know. So this is a relatively recent observation, and twisted bilayer graphene, much needs to be understood about it, but it definitely shows a clear-cut regime of Planckian behavior with linear resistivity. So at this point, it's speculation on what is causing it. So my proposal is that, in fact, from our studies of Fermi surfaces coupled to low energy degrees of freedom, we are finding that the only way you get this kind of behavior is by having some random interactions. And so, yes, my hypothesis would be that there is some randomness here in these systems, more than the experimenters probably admit. There are all kinds of grain boundaries and maybe fluctuations in the twist angle and who knows what else. And that randomness is important for the linear resistivity. Now, of course, one way
it couldn't just emerge from the randomness in my interlayer coupling, because when you're at the small angles, you could have all these undulations and.
Absolutely, it could come from that. Yeah, that's a good suggestion.
Yeah.
Yeah, I mean, of course, the way to test this is to get a system without any randomness, which I think is easier said than done, but and see if this behavior disappears. I mean, you'll even have randomness on the edges of the samples, on the leads. That may be enough, so it's really hard to get rid of it completely, and we think it's quite important. I don't think, there may be others who disagree with me, but I think, yeah, this is what's, from our studies, that's our proposal anyway.
Thank you.
Sure.
Any other question?
Yes, Manoranjan, I want to ask some questions.
Yeah, please go ahead.
Yeah, you mentioned that the theories with random couplings results in Green's functions. They have some specific structure, and also it results in maximal chaos. And
yes.
What I observed was that the result for the Green's function for the SYK, as you mentioned, and also for the random TJ model, they were looking the same. So is it true that with theories with random couplings, these Green's functions, the structures for the Green's functions and Lyapunov exponent is universal in some way?
In theories without quasi-particles, yes. Oh, sorry, somebody needs to turn off to mute yourself.
Sunandan, please mute yourself.
Yeah, so I would say that. Okay. So in the SYK model, you have this Green's function here. Yeah, this Green's function here with some power of frequency and a function of h power 1 omega t. So that's a feature of a model that has very strong interactions and no quasi-particles. if I took the other model, if I took this model,
Yeah.
free Fermi model, the Green's function, this model does not obey that.
I see.
Yeah, so it doesn't have scaling, it doesn't have any singularities, and for the for the Fermi surface coupled to a scalar problem, then this one you have to be at the critical point if this is an order parameter, or if it's a gauge field is generic, and this behavior here is only at the Fermi level, k equals kf. If you take some other momentum, it's a little bit more complicated. Yeah, so it is quite generic if you have a system without quasi-particles. That's certainly the that's, I don't have a proof of that, but I think that's a pretty reasonable statement. Now, whether the other part of your question is whether this leads to maximal chaos, may not. It could be something number smaller than 2 pi here in other systems. It's curious that that's what came out as exactly maximal, and also in this non-Fermi liquid, it's exactly maximal. This is an unpublished result, I should say. We're a bit surprised that it's exactly maximal, but yeah, okay.
Does it indicate something?
Yeah.
That the fact that it corresponds to, it gives you a maximal chaos, a maximal value of the Lyapunov exponent. Does it indicate something?
Yeah, so there's
some special symmetry.
Yeah, no, not a symmetry really, but okay. There's a very nice paper by Gu and Kuter.
Okay.
Okay.
And also you mentioned
where
that
they show that if you have a space-dependent system,
yes,
then the butterfly, if the butterfly velocity is large,
And then please mute yourself.
yeah. So if the butterfly velocity is large, then you will get maximal chaos. And so what we've done in our to disappear work is actually what we really do is a careful computation of the butterfly velocity and find that it indeed satisfy the required inequalities to give you maximal chaos. Yeah, I think that there's a conjecture effectively in the paper by Gu and Kuter that it may well be that at long enough distances in a wide class of system, chaos is exactly maximal. There's no proof of it, but that is something worth further study.
Okay, so
But this is something very, very hard to study because you need. Sorry, go ahead.
Sinandan, it's okay now, right? Yeah, so
I just had one more question. Yes.
okay, it
I
will be the last
question.
interview. I hope. Yeah.
Yes. You also mentioned that the gravity dual of this SYK model is ADS2, which came from the Rising-Nordstrom, the near horizon geometry of the Rising-Nordstrom black hole. So my question is there a gravity dual for the random TJ model also? Is it known?
Well, no, it's not known. And then the random TJ model at low enough temperatures probably doesn't have a gravity dual because it becomes either a spin glass or a Fermi liquid. If you take the large M limit, the SUM large M limit, which is in fact the original model that was studied by myself and Jin Wu in 1993. If you take the SUM TJ model in the large M limit, we did only the SUM J model, but you could also take the SUM TJ we did recently with Darshan Joshi. Then yes, I mean the dual, to the extent that the dual is still ADS2. So ADS2 plus a scalar is with JT gravity. ADS2 plus a scalar is with JT gravity. Yeah.
Okay.
Okay, so let's take another question from Mukulla. Mukul sir, please go ahead.
Thank you. So, let me thank you for a very nice talk. I had one question, which is basically that random TJ model you talked about, and the propagator with the omega over T scaling that you obtain is basically reminiscent of what you would get in a scenario of Kondo breakdown in Anderson kind of model. Within extended dynamical mean field theory, for example. So, for example, Antoine and others have sort of done it in various forms. So the point is, the question I had was if one would relax the constraint of all-to-all coupling, would one still obtain a propagator with a fractional power law form and omega over T scaling?
Okay, good question. So first of all, when you say Kondo breakdown, do you mean a Kondo lattice model or a Kondo impurity model? Because the situation is quite different for the two of them. Hello?
I mean, if one put the random TJ model on a Bethe lattice, for example, and did an extended dynamical mean field theory, would one get a linear resistivity?
Yes, you do. Yeah. In fact, that's already been pointed out by Bernard, Grempel, and George. Yeah, you do. So that's a slightly different model, but yeah, so they take essentially an SYK model on the J sector. And then you couple it to the fermions hopping on the beta lattice, and you get a linear T resistivity. Yes.
Thank you.
Okay.
Sure.
Is there any other question? If not, then let's thank the speaker for excellent talk. And thank you very much, sir, for joining us today.
Thank you for inviting me.
Thank you, sir. Thank you.
Okay,
See you.
bye.
Bye.